Hello dear viewers, this time it's about acetylene, the most energetic hydrocarbon gas. In the first half of the last century, so-called carbide lamps in which acetylene was generated and burned directly were used as hand, car and bicycle lamps. Today acetylene is still of technical importance in welding because very high temperatures can be achieved with the gas due to the high carbon content and premixed with pure oxygen. And it's still one of the most important precursors in the chemical industry. Today we examine the chemical properties of acetylene, and yes, the energetic ones are also part of it. So stay tuned and have fun watching. Anyone who knows this channel already knows this obligatory warning. If this is your first time here, please skip back and read it carefully. First we prove the multiple bonds of the unsaturated hydrocarbon. For this we use the so-called Bayer's reagent, a highly diluted potassium permanganate solution made alkaline with sodium carbonate. We generate our gas directly from calcium carbide, great chunks that combined with water form acetylene and calcium hydroxide. Pure acetylene is nearly odorless. However, our technically pure carbide contains impurities which with water releases traces of highly toxic phosphine, which has a garlic-like odor. Even if the amounts of phosphine are very small, the experiment should only be carried out with good ventilation or outside, if only because of the extremely highly flammable acetylene. The gas is now introduced into the Bayer's reagent with an angle pipe connection. The violet solution loses its color and precipitate of manganese dioxide forms. In turn, alkenes are oxidized to carboxylic acids. Accordingly, oxalate should then be present here in the alkaline environment. However, we aren't entirely sure about this, especially since we haven't found any information about the reaction product in the literature. If you know it for sure, please let us know in the comments. Another test for unsaturated compounds is the decolorization of bromine water. In an addition reaction with acetylene, dibromoethane is formed first and then tetrabromoethane in a second step. The addition doesn't proceed as quickly as with alkenes. Carbide has to be refilled a total of 4 times before all of the bromine was converted completely. A clear colorless watery liquid remains. Because of their high density, the bromohydrocarbon products form a droplet collected at the bottom of the test tube. According to information in the literature, however, the product should be more of a brownish to reddish color, which wasn't recognizable here. It rather forms a milky cloudy liquid, which could be caused by its water content. In the next step we look at the combustion behavior of acetylene, which we produce again directly from calcium carbide and water. For good reason, we rarely use glassware. To generate the gas, we fill the plastic bottle at least half full with water, put some steel wool in the exhaust nozzle to prevent backfire, and replace the pop gas test with waiting a few seconds for all air to be expelled. Because if air was still present, the subsequent explosion when the gas ignites could easily shatter any remaining glassware used. Because of its high carbon content, acetylene burns in air with a bright and very sooty flame. What happens when an acetylene air mixture catches fire can be demonstrated with the following experiment, which isn't unspectacular, but relatively safe, provided that the scale and safety precautions are observed. It's about to get loud. Hearing protection strongly recommended. Under no circumstances may the batch be enlarged or the experiment carried out with pure oxygen instead of air, otherwise you might risk your life. A few small pieces of calcium carbide were placed in an empty tea light holder. More shouldn't be used, otherwise the gas mixture will become too rich and won't ignite properly the way we want him to do. Then some water is added, which releases the acetylene from the calcium carbide. The empty potato chip packaging roll is put over it. The previously cut open end is loosely covered with a plastic lid. Then you have to wait a few seconds until enough gas has formed and distributed in the cardboard cylinder. The acetylene air mixture emanating from a small hole previously drilled in the side of the roll is then ignited with a stick lighter. And because it was so nice, here it is again in slow motion. Acetylene spontaneously ignites in direct contact with chlorine. We demonstrated that in this earlier experiment by dripping semi-concentrated hydrochloric acid onto a mixture of calcium carbide and calcium hypochlorite. If you would like to see the complete video with the associated explanations, simply click on the link at the top right. To never miss another video, subscribe to the channel and activate the bell if you haven't already. Thanks for watching and see you soon. Bye.